Hello everyone, welcome back. Let's talk about another medium problem on Leetcode today. Lowest common ancestor of a binary search tree, Leetcode 235. In this problem, we are given a binary search tree and we have to find the lowest common ancestor LCA node of a two given nodes in the binary search tree. According to the definition of LCA on Wikipedia, the lowest common ancestor is defined between two nodes P and Q as the lowest node in the tree T that has both P and Q as descendants, where we allow a node to be a descendant of itself. Now, in terms of constraints, we are given that all the node values in the tree are unique and both P and Q exist in the tree and P is not equal to Q. Now, let's take some examples. For this given tree, suppose P is equal to 2 and Q is equal to 8. And we can see that node 2's ancestor is 6 and node 8's ancestor is also 6. So node 6 is the only common ancestor and also the lowest common ancestor of both nodes 2 and 8. Now let's take P is equal to 0 and Q is equal to 5. And in terms of definition of lowest common ancestor is defined as the lowest node for which P and Q are descendants. And visually we can see that that node is node 2. Another way to say this is that ancestors of 0 are 2 and 6 and ancestors of node 5 are 4, 2 and 6. So the lowest common ancestor here is node 2 because it is at the deepest level when it comes to binary tree and is ancestor of both 0 and 5. Even though root node 6 is also a common ancestor, it is not the lowest one. So in this case we will return 2 as our answer. And now let's take example 3. Suppose P is equal to 2 and Q is equal to 4. Here node 4 is descendant of node 2 and according to the LCA definition, a node can be a descendant of itself. So node 2 is also a descendant of node 2. So that's why lowest common ancestor of both nodes 2 and 4 is 2. In terms of solution, we can solve this problem similar to how we solved it for a binary tree. That approach does not utilize the properties of binary search tree, where nodes in the left subtree of a node are less than the node and nodes in the right subtree are greater. But if you are interested in the lowest common ancestor for binary tree solution, please check out the I button. Now we try to find the lowest common ancestor for P equal to 0 and Q equal to 5 in this given binary search tree. And we again started the root node. Why? Because the root is always the common ancestor of every node in the tree. So the root is common ancestor of these two nodes as well. But we do not yet know if it is the lowest one. Now both the values 0 and 5 are lower than the root node 6. Hence LCA cannot lie on the right side because in a binary search tree all the values on the right will be higher even than 6. So both the nodes and their LCA will lie on the left side of the tree. Now we come to node 2 and the value of node 2 is between the values 0 and 5, which means node 2 lie between these two nodes 0 and 5. And this is where the split happens. So node 2 should be the lowest common ancestor. Because if we go towards left and choose node 0, then it will be ancestor of node 0 but not of node 5. Similarly, if we go towards right and select node 4, then it will be ancestor of node 5 but not of node 0. So that's why node 2 should be the lowest common ancestor between the nodes 0 and 5. Let's take one more example with P equal to 2 and Q equal to 4. So again, we start at the root node. And since both 2 and 4 are less than the root, we go towards the left to find them. And now we come to node 2, which is equal to the value P here. If we find either of the node while searching for P or Q, instead of the split that we saw earlier, then that node should be the LCA. So this time 2 should be the LCA because a node is allowed to be a descendant of itself. So node 2 will be the ancestor of itself as well as node 4. And if we go lower than this, say suppose we go towards node 4, we will find the ancestor for node 4 in node 4, but it will not be ancestor of node 2. So for us to find the lowest common ancestor, the node should at least be an ancestor, right? So node 4 cannot be the lowest common ancestor of both node 2 and 4. And it is guaranteed in this problem that both P and Q exist in the tree. So even if we couldn't find node Q in this case, it should be somewhere deeper than P. Hence, we don't have to find Q to determine the LCA in this case. Therefore, in such cases, whichever of the nodes P or Q we find first, we will return it as LCA. And in this example, it is node 2. Now let's code it up. First, we check the base case. That is, if root is null, then we will return null. This means that we have traversed beyond the leaf nodes in the tree and hence we should return. Then we will check if both P and Q are less than the current node's value. If that is the case, then we should search in the left subtree. But if both P and Q are greater than current node's value, in that case we should search in the right subtree. Otherwise, if both P and Q lie on the different sides of the current node, or if one of the values P or Q is equal to the current node's value, then we should return the current node. Now let's submit this code. Cool. In terms of time complexity, it will be O of h, where h is the height of the tree. And in case of a balanced binary search tree, it will be log n. And the reason for this is, at each level of the binary search tree, we compare the current node's value with P and Q to decide whether to search in the left or right subtree, effectively checking only one node per level. This process continues down to the depth of the tree. Hence, the time complexity will be O of h, or O of log n in case of a balanced binary search tree, or O of n in case of a skewed binary tree. And in terms of space complexity also, the depth of the recursion corresponds to the height of the tree. So it will be O of h, or O of log n in case of balanced search tree, or O of n in case the tree is skewed. And now the question is, can we do better? And the answer is yes, we can do better in terms of space complexity, but the time complexity is already quite good. And the way we can save space is by converting this code to iterative one, because then we won't need the recursion stack. So instead of ending our search when root is equal to null, we can check if root is not null and continue our search until we reach the depth of the tree. And now we can move this code inside the loop, but we still are making the recursive call. So instead of making a recursive call to the left, we can just go to the left. And similarly, instead of recursing on the right, we can just move towards the right and return the root in case we found a split point or the value is equal to either of P or Q. And in this case, we should also return null from here. Otherwise, the compiler will complain. But if the binary search tree is valid and test cases are rightly generated, then we shouldn't reach here. Now let's submit this code. Awesome. Now the time complexity is still O of h, but the space complexity is O of 1. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.